Afternoon, everyone, or morning, depends where you are. Welcome to Taco Tuesday. My name is Brett Zerba, and I will be moderating today's discussion / webinar. The main presenter will be Rich Medairos. Based on looking at the attendees, most of you have been through this before, so you kind of know the routine. Today's topic is very interactive, so please, as always, ask your questions. I'll be moderating them and looking at them and bringing them up as I can. If a couple of you can wave your hand to make sure we can see, you can hear and see me. I don't see any hand waving yet. Oh.
So whatever's going on, Brett, I can no longer hear you.
The recording of today's webinar, as well as access to your PDH certificate, if you so need one for your continuing for your to help with your hours for your professional development for engineering. Anyways, that's about it for today. Oh, there is one handout. We just added it, so hopefully you can see it. There is a handout, commercial troubleshooting, pump troubleshooting guide. Rich will get into a little more details of exactly what it is, but nonetheless, there is a handout. Rich Medairos will introduce him. Can anyone hear Rich?
I haven't.
Rich, I can't hear you.
You keep fading in and out, Brett.
Okay.
Let's try this. This is Rich.
Okay.
Let's see if everyone can hear me.
I apologize. Rich, take it away.
So
I hear Rich.
Okay, Darren says he can hear me. Everyone can hear. Okay. Well, must be at your end,
Yep.
Brett. Whatever's going on is going on at your end.
Yep.
So in the question area, well, a lot of people are saying they can hear me loud and clear, so that looks good. So I'll get started. Just a quick intro for those who have not met me or haven't been through one of these before. I'm one of the senior systems engineers here at TACO, and I get involved with a variety of training exercises. Brett and I team up, and we do these webinars. We do the TACO Tuesday, we do the TACO After Dark, we do custom presentations for different folks that are out there. So today is all about troubleshooting, and in a minute I'm going to start my discussion. Just another quick note, I am a mechanical engineer. I specialize in the engineering design of HVAC systems, and I've been at this for a couple of years. So today's topic, as it says, and I tried to create this crazy alliteration, top 10 TACO troubleshooting tech tips. I call them the 6 T's. And we're going to talk a little bit about the process, and we'll have a specific example that we'll go through. And if we have some time, we'll try 2 different pieces of equipment. But initially, we're going to talk about some pump issues. So anyway, I'll try pressing the button here. That works. There we go. All right. So what are my top 10 troubleshooting tips? So stay calm is the first one. Identify the problem. Interview the customer. And I'm going to go through each one of these in detail so you'll see where I'm headed with this. Develop a plan. Request a piping diagram if at all possible. Assemble manufacturer's data. Collect field data. Analyze the data. Calculation review. And recommend a solution. So let me give you a little background before we go into the meat of this discussion. So the folks that are out there listening today, you might be in a variety of different troubleshooting positions. I will tell you a little bit about the position that I'm in, and yours might be similar, but the process actually works the same. So in my case, I usually get a call from either one of our reps, or I get a call directly from a customer. And depending on where the customer is in the country, I will pull our rep into the conversation. And then I usually go through these 10 different steps here to see if we can come up with a solution for them. But you might be, for example, you might be working in an engineering firm and your customer might be the mechanical contractor, and it doesn't necessarily have to be a TACO issue, but it could be almost any kind of issue. So the contractor would be the customer in that case, or you might have an owner that has a problem, you're trying to help them solve the problem. So it's a variety of different positions, but the process is pretty much the same. So usually it starts off, let's assume for a moment that I get a call directly from a customer, and I'll either get an email or they'll actually call me on my cell phone. And usually it's a kind of a panic situation. So the first thing I try to do is to try to get everyone to calm down, because the only way we can get through this troubleshooting process is to stay calm and work through the problem. So as part of that process, the first thing I do is introduce myself. So again, let's start off with, we get a call. Let's assume I get a call on my cell phone and someone says, you know, I'm Acme Contracting Company. I'm working out here in Salt Lake City, Utah, and I have a problem. And can you help me out? And you know, and I have a major problem. I've got whatever it is. So I start off by introducing myself, and to try to reach some common ground here. I also when I say tell them about you, in this case, I'm telling them about myself, and I usually start off and say I'm with TACO, and I'm here to help. So it's very simple and straightforward. We want to try to reach a common ground. We want to stay calm. We want to try to approach this methodically. So introduce yourself, tell them about yourself. In my case, I might say I'm a mechanical engineer. I have a background in engineering design of HVAC systems, and I've done quite a bit of troubleshooting, and I'm here to help, and I'm with TACO, that sort of thing. Okay, what's the next thing we want to do? We want to identify the problem. So in this particular case, I get a call from a customer where we've gotten through the initial introduction part. I know who they are, they know who I am. And before we go any farther, I just want to make sure I understand exactly what the problem is. And so I asked them, you know, can you tell me in very short what is going on? And for this particular case, the customer says, I have a chilled water system and the water flow is low, and I'm sure that it is the pump. It's not necessarily the pump. It could be the pump. It could be something completely different. So let's, the problem here, we want to differentiate between an individual piece or component in the system, but the first part of this discussion is really, they have a flow problem, and we don't know if it's the pump. They may think it's the pump, but we don't know that yet. And so we're going to try to work through this issue. So we've identified the problem. There's a low flow condition in a chilled water system. Okay. So now I go through the interview process. I need more information, because when someone says they have a chilled water system, that could be a variety of different things. So I usually try to narrow things down by asking some specific questions. Is this a water-cooled system? And let's see, what is their answer in this case? The customer comes back and says, yes, it's a water-cooled system. Okay, so I know it's a chilled water system, and it's water-cooled versus air-cooled. And so the question is, next, is the issue with the chilled water side of the system or the water-cooled or condenser water side? So I try to identify that. Is the problem with the chilled water or the condenser water? You can see we're trying to narrow things down here. So we get down and the answer is condenser water. And I said, okay, fine. We have a condenser water problem. We're starting to get a little bit more information. How many pumps are in the system? Well, they come back with their answer and they say, well, we have 2 pumps. Great, so now we know it's condenser water, it's 2 pumps, and the next question I ask is which model TACO pump? And in this particular case, they came back and they said it's a TACO model FI 5011D as in David. And for those of you that may not be familiar with our model designation, that is a base-mounted end suction pump. And it's the latest version because it's a D as in David version. So I know it's a fairly new pump. By the way, I asked this question, this came up, this is kind of funny, this came up about 3 years ago, I think it was. I was talking to a customer and they were going through this process and I was asking the different questions and I said, which model TACO pump is it? And they said, well, it's not actually a TACO pump, it's another manufacturer. I won't mention the other manufacturer. And I said, well, why didn't you call the other manufacturer? And they said, well, they said they didn't know much about systems. They could only talk about their pump. And so I said, well, I'll help you with your problem and hopefully we can identify it. So I got involved with working on a problem that was not a TACO pump. But for the most part, if we're with TACO, we like to help people solve problems if it's TACO equipment, but every so often it's not. Okay, so we've identified.
So it's true. It's true, Rich. You are a nice guy.
Well, you never know exactly what the issue is, and you know, it could be. In other words, it's not necessarily a pump, but it could be a pump. But if it's someone others, yeah, I'm sorry. If it's some other manufacturer, if I narrow it down to potentially a pump problem, I have to stop there and say, look, we've narrowed it down. We believe it's something to do with the pump, and now you have to talk to the pump manufacturer. But maybe it's not the pump at all. Maybe it's a system issue, and sometimes we can help people out. Okay, so that's part of the interview process. I have a few more questions for this person. What are the design operating conditions? And in this particular example that we're talking about today, let's assume the customer comes back and says, well, it's 1,000 gallons per minute at 80 feet for each pump. So you've got 2 pumps in the system. It's condenser water. Look, we're getting all kinds of information by just going through this interview process. And the pumps are connected in parallel. I don't know that yet, by the way. He just says he's got 2 pumps. And they're 1,000 gallons per minute each. That's how each pump is rated. So, and so then I said, well, what are you measuring for flow? Now, well, the design condition we just said was 1,000 gallons per minute, and they come back and they tell me, well, they're measuring 750 gallons per minute. Now, we still don't know exactly what the problem is, but we're starting to narrow things down a bit. So I said, are you taking measurements with 1 or 2 pumps operating? Now, this is an extremely important thing because if you have 2 pumps operating in parallel and you have the operating data for 1 pump, then you need to just run 1 pump. Now, that's not always, you're not always allowed to do that because of existing operating conditions, but if at all possible, run 1 pump so we can determine the operating conditions of 1 pump as opposed to 2 pumps running in parallel, because it gets a little more complex when we're trying to troubleshoot 2 pumps running in parallel. So we have to establish the performance of 1 pump. So they took the measurements on 1 pump, so that was a good thing. So now we know we have the data that they've given me so far is 750 gallons per minute, and there's 1 pump operating. Okay, so the next key question is, how are you measuring the flow? And you know, the preferred method is usually a calibrated flow meter that is either permanently installed in the piping system or it's a non-invasive flow meter, like a strap-on flow meter, ultrasonic flow meter, or something on that scale. In this particular case, however, the customer came back and said, well, we measured the delta P and we looked at the pump curve. Well, that gives us an indication perhaps of what's going on, but it doesn't necessarily tell us that that's actually what the flow is. So, but we put that in our basket of information that we've collected. And so I say, well, what was the delta P that you measured when you looked up the flow on the pump curve? And they came back and they said, well, the delta T was about 92 feet. So now we have some data that hopefully it'll be of some value to us. Okay, so the next step is really to develop a plan. So what do I want to do for a plan? Well, the first thing I'd like to do is I'd like the customer to take a whole series of photographs. By the way, you can never have enough photographs when you're troubleshooting. Because everybody has a smartphone today, it's easy to get photographs and it's easy to have those photographs forwarded over. So if you're ever worried about how many photographs to take, you can never take enough. So ask the person who is physically out on the site to take as many photographs as possible and get them over to you as quickly as possible so you can review them. It'd be nice if you could review them in real time. So in other words, if they're out at the site, it's 11 o'clock in the morning, you say, could you take a whole bunch of photographs for me and then send them to me? And while you're on the phone with me, I'll go through those photographs to see if there's some other piece of information that would be of value to me. And usually people are very cooperative, by the way, and they help us out. So they take lots of photographs. The other thing that we would like to have on our plan is we'd like to have some piping diagrams. Now, piping diagrams, if it's a fairly new, let's say it's a brand new installation, there should be one-line diagrams for the piping system as part of the contract documents. But a lot of times we're asked to troubleshoot things where the documents have disappeared long ago. They don't have them, in which case I ask for a hand sketch. So between the photographs and a hand sketch will give me a pretty good idea of how the system is arranged. What else do I want? Oh, that's what I mean, a piping sketch. So a hand sketch or a piping sketch. I'd also like to collect some electrical data. And I'm interested in the volts and the amps at the motor input. Now, here's where the challenge comes in. If it happens to be a variable frequency drive, the voltage and the amperage, well, the voltage specifically is modified by the variable frequency drive that's delivered to the motor, in which case we would like to collect the volts and the amps at the input of the variable frequency drive along with the speed that the variable frequency drive is running at. Now, in this particular example that we're talking about today, we're interested in the data that they collected at full speed. So when they told me they collected 92 feet of differential pressure, I also need to verify that they did that at full speed. In this particular example, I think it's 1760 RPM, but we'll check that in a minute once we go through the data. So I also want to check the RPM and the rotation. Some people will actually, that'll be the very first thing they ask for. And sooner or later, I'm going to ask for the RPM and the rotation, just to make sure that the pump is operating at the right speed and it's operating in the right direction. Okay. Here's what a piping diagram looks like on this little job. I'm looking at the condenser water right now. And Brett, I know that we're having some audio problems, but Brett, can you see the bouncing ball?
I can. Can you hear me, Rich?
I can now, yeah.
Okay, good.
Loud and clear. Do we have any questions yet, Brett?
Okay, well, William said, confirming what you just said, the voltage will be less than line when the VFD is reduced, is at a reduced hertz?
Okay, so when the variable frequency drive sends the voltage to the motor, it varies the voltage as a function of speed. And I believe the voltage is reduced, but don't quote me on that. If someone else there knows that answer, that would be a good little piece of information. I believe though that if the drive is sending out information to the motor, I believe it's reducing the voltage, but someone could help me out with that. That would be great.
I'll let you know if someone types it in.
Okay. So we have a little diagram. This is what they gave me initially. And it looks fairly straightforward. I have two. Now I can see that the diagram is telling me that the two pumps are piped in parallel. Each pump is roughly 1,000 gallons per minute at 80 feet. And the diagram indicates that there's really nothing between the cooling tower, in this case, it's an open cell cooling tower, and the inlet to the pump other than an isolation valve. At least that's what the initial information is all about. Now, again, if the piping diagram exists, that would be great if they could send that over. If it doesn't exist, a hand sketch would be helpful. The hand sketch or the piping diagram in concert with the photographs really helps us understand how these things are configured. So in this particular case, it looks like, let's assume that the photographs match this diagram for a moment. Actually, there is some pieces of information missing, but let's see if we can narrow it down. Let me get rid of my bouncing ball here. Okay. And this is just the chilled water side of the diagram. So the first diagram I showed you was the condenser water, and these two lines up here that show the chilled water going out at 42, coming back at 54, and then the rest of the diagram, I split it up so it'd be easier to see. But we're not interested, they're not telling me they have any problems with the chilled water side, just the condenser water side. So I'm gonna kind of ignore this half of the diagram. Okay, the next thing is I'm looking for manufacturer's data. And that's why it's important to get lots of photographs, because in this particular example, we're troubleshooting a model 5011D, an FI, that's an end suction pump. I'll show you a photograph of what that looks like in a minute. But you'd be surprised at how many times people will tell me that they have a certain model pump, and then they'll send me a photograph of the pump tag, and it doesn't match what they told me. So that's the other important reason for getting photographs, to make sure that the pump model that they assume is out there is in fact the pump model that we're looking at. So actually this came up not too long ago, a couple of weeks ago. Someone said that they were having some issues with an FI base mounted pump, and when they sent me the photograph revealed that it was a vertical inline, and the model number that they originally gave me was incorrect, but they did have a photograph of the pump tag, and so we were able to get the our manufacturer's data in this case. So what kind of data do is the manufacturer have available? Well, the most important one is the pump curve, but in this particular case, we're also interested in the installation operating manual. So I have examples of both here on the screen. So the one on the right, I get my bouncing ball again. The one on the right is the installation and operation instructions, sometimes just referred to as IOMs, and then the pump curve. And I may actually, if it's a Taco product, I may do also some research on my own to see if there's other data that may be valuable to me. But these are just examples of the kind of data that you need to collect. Okay. All right. So what's the next thing we need? We need the field data. And this is just a picture. I know you can't see it very clearly because it's fairly small. But this is actually in the handout, and we call this the commercial pump troubleshooting report. And this is usually the minimum amount of data that we like to collect. I'm sorry, in the field. And since this is a downloadable handout, you can get a copy for yourselves right from the website today. Okay, Brett. Before I go too much farther, before I start digging into this in some detail, any questions out there?
Nothing right now, Rich.
Okay. Okay, so the next step in the process is to analyze the data. And I'm actually going to go through a specific example that we talked about, and I'll show you how we go through the analysis part. And then also, so yeah, let's get into it a little bit. So let's analyze the data. So let's look at the pump that is in question here is an FI 5009D, as in David. Is that the one I had in that diagram? 50, oh, look at that, Brett. I had a 5011D.
Right.
So let's assume for a moment, I'm actually going to change this in real time. I'm going to pretend that this is a 5011D. That was pretty cool, huh, Brett?
That's how quick you can change it in the field, too.
I don't think so. Okay, so we got a 5011D. That's pretty much what it looks like. And this is the pump curve that goes along with that. And they told us for a single pump operation, it's 1,000 gallons per minute at 80 feet of head. And the red line represents the pump curve and the blue line represents the system curve. Now, today's discussion is not to get into the details of how to read a pump curve, but it's going to help us with the troubleshooting process. Now, if you recall, they said that they didn't actually measure the flow. What they did was they took the pressure differential across the pump, and they said that that pressure differential was 92 feet. So if I go over here, I'm going to draw a line here. Let's see if I can draw this without, what color is my line today? Ooh, that's a weird color, huh?
It's a little different.
Yeah, so let me change the color of the pen. Oh, there. How's that, Brett?
Good.
Okay. So
Brighter.
what I'm going to do is I'm going to take the field data that they gave me and they said, well, we've got, they measured a pressure differential of 92 feet. So if you'll notice, this line here is 80 feet, there's 80, and there's 100. So halfway between those two is 90. So this horizontal line is 90. And if I come over here, you can see that I'm going to try drawing a horizontal line right across here. And you can see that if it was 92 feet, it would be right on the pump curve. And so the actual flow, which they told me was 750 gallons per minute, is in fact a pressure differential of 92 feet. So what are we really talking about here? And here's one of the things that we have to make sure we do properly here. Okay, so the pressure differential of the delta P across the pump, that's from the suction to the discharge. But to get the true delta P, we have to make a correction for the pump size, because the inlet on an end suction pump is generally larger than the outlet. So that means if there's a pipe that's connected over here, let's say it goes up into the system somewhere. There's the pipe. I don't know, that's kind of a cool looking pipe, right, Brett?
Yeah, that's a good picks. Good pick.
Yeah, it's hard to see, but there is a connection for doing a pressure reading across the pump. And what we have to make sure is that we correct for the velocity. And in this case, the outlet velocity, the outlet of the pump is smaller than the inlet, and so the outlet velocity is going to be greater than the inlet, and so we have to make that correction. So if we take the data at the outlet velocity, then we have to correct that outlet velocity for the delta P, so we get the accurate delta P. So let's assume that they did that correctly, and they gave us the corrected value, and it was 92 feet. Well, at 92 feet, which we said was roughly here on the curve, that's 92 feet. Let me erase some of these lines because it might be a little bit too confusing. So I'm going to go 90, this is 90, and I'm going to go just above that and kind of draw a horizontal line, and that's going to intersect the pump curve. And so they're telling me that they measured 92 feet, and that's how they came up with 750 gallons per minute. Now, what we would prefer to have is we would prefer to have the flow measured independently so that we could check it. So again, we would prefer to have the flow either through a calibrated, permanently installed flow meter, or like an ultrasonic, non-invasive ultrasonic flow meter that's been recently calibrated. Because we really do need to understand what the relationship is between flow and head. Now let's assume for a moment that their data was correct, that the field data was correct, and that they're actually getting 750 gallons per minute. But the pressure differential across the pump is 92 feet instead of 80 feet. So now we have a problem. We say, well, initially, the customer may have thought that we have a problem with the pump, but in reality, it's starting to look like there is a system issue somewhere, because we are actually operating on the pump curve, but at a different pressure drop. So I'm going to go over here and get another pen here. I'm going to draw another system curve. Now, in this particular case, I'm going to draw a system curve from here. Whoops, didn't do that real good, did I? Let's say that that's not the best system curve in the world, is it? Let me try this one more time. And start off here And I want that to go up here. Well, that's not the best system curve in the world. So in reality, it's beginning to look like this is the actual system curve over here and not what they originally designed to. So what could potentially be causing the problem? All right, so let's keep going here for a moment and see if we can't narrow this down. So we're going to erase this a little bit. Now remember, they sent me a piping diagram, and they also sent me some photographs. Whoops. There I go. Sorry about that. Okay. So what kind of data did they give me? Well, they gave me the pump data. I'm sorry, they gave me the pump curve, and here's all the data that's available to me from the pump curve. It says that at the design operating point at 1,000 gallons per minute and 80 feet of head, my brake horsepower is 23.5 horsepower. That comes right off of the pump curve right here. But they're telling me they're running around 75 gallons per minute, and it's around 92 feet. So that means that my horsepower should be closer to, in this particular case, fairly close to 20 horsepower. So maybe the actual horsepower at this point is, say, 21 horsepower. So how can I find out how much horsepower? So this is a question for everybody in the audience. How can I actually figure out what the horsepower is? What kind of data? Let's assume for a moment that they've given me all the data that I've asked for. And out of that package of data, how can I figure out how much horsepower the pump is consuming? Does anybody have any ideas out there while we're looking at this pump chart?
Eric said the VFD readings. Heidi said volts and amps. Another Eric, electrical input, VFD, pump affinity laws. That's our friend Darren McPherson, I think.
Well, the easiest thing to do is, let's assume for a moment, we have two cases. Let's take case number one. There is no variable frequency drive.
On the curve, someone said.
So we're going to actually take the field data and we're going to calculate the data. And how do we calculate that data? Well, let's assume the first case is there's no variable frequency drive. And I usually ask for an electrician to measure the data because I don't want to start fiddling around with wires and electrocuting myself. I'm not a licensed electrician. So usually I ask the contractor to have a licensed electrician take some data. And I want him to take, without a variable frequency drive, I want him to take the volts and the amps at the input of the motor. And let's assume in this case, this motor has already been confirmed. It's rotating in the right direction and it's rotating at 1760 RPM. Let's assume that they've done that. And now they give me the volts and the amps. And I use the following equation. I take the volts times the amps. And on the nameplate of the motor, it'll show me, which is why photographs are so important, it'll show me what the efficiency of the motor is and what the power factor is. So if I want to find out how much power the pump is consuming, I would take the voltage times the amperage, and if it's a three-phase motor, I'd multiply by the square root of 3, and I'd multiply also by the volts times the amps, and I divide by 1,000 because volts times amps gives you watts, and I have to convert that into kW, so I divide that by 1,000. And that would give me the kW, and then I have to divide that once more by 0.746 to convert it into horsepower. And if the horsepower came out to roughly 21 horsepower, then I know that I have another piece of data that's confirming, that's starting to point to the fact that the reason I'm not getting the flow is because there's more resistance in the system than what was originally anticipated. I can also ask for the shutoff head. If you notice on the left-hand side here, I can ask them to do the shutoff head test. And if you'll notice, I put in plus or minus 8 feet because the shutoff head can actually be greater or less than the published value by as much as 8 feet. So in this particular case, if they throttle back on the discharge valve, never the suction valve, always the discharge valve, and they isolate it for a few seconds, they should be able to measure the pressure at the pressure differential across the pump. And in this case, the shutoff head should be around 97 feet, which will confirm that the impeller diameter is what we had originally anticipated. And then the last thing that we can get from the pump data here is the pump curve is the net positive suction head required by the pump. In this case, it's approximately 9 feet of water column. And again, the units for net positive suction head required by the pump is 9 feet water column absolute. So these are absolute pressures up here. So I have more information. So that's how I was able to collect all that data. All right, let's move along here for something. So I'm going to start doing some calculations, and I'm going to actually do a calculation on the net positive suction head available versus the net positive suction head that's required. So we just said from looking at the pump curve data that the required NPSH is around 9 feet. I also figured out what the power consumption was by taking the readings of the voltage and the amperage. And remember what I said in the first example, let's assume that it did not have a variable frequency drive. If it did have a variable frequency drive, then we'd want to we'd want to measure the voltage and the amperage at the input of the drive. And then when we do our calculation, we have to include the inefficiency of the drive, and that's how we can arrive at the power consumption. So if you recall, I said we take the volts times the amps if it's a 3-phase motor times the square root of 3, and then multiply that by the pump efficiency, the motor efficiency and the motor power factor. And if there's a variable frequency drive involved, we'd also have to multiply that by the drive efficiency. And again, the simplest way to do this is at full speed or 60 hertz. We also want to know what the pump efficiency is. And when we do our calculation review, we'd also make a correction for the velocity. Because remember that the outlet velocity on an end suction pump will be higher than the inlet. The overwhelming majority of end suction pumps. I don't know if that's true 100% of the time, Brett. Maybe someone out there in the audience could tell me, but at least I think in our base mounted end suction pumps, our inlet is always larger than our outlet, so you'd have to make a velocity correction. And you'd also have to make a pump speed correction because the pump is tested at 1760 RPM, but not all electric motors will spin at full load at 1760. Some might spin at a higher speed, especially some of these premium efficiency motors. They might actually spin at 1780. I've seen some at 1785 RPM. So the more efficient the motor is, the higher the rotational speed. So if there's a higher speed, it has to be corrected for the speed. Okay, now we've got all of that data, and now we need to recommend a solution. We've done all of our research and stuff, and everything that I've done so far has led me to believe that I have a pressure drop in the system that is greater than what was originally anticipated. And so I look back at one more time, I take another look at the piping diagram and the photographs, and lo and behold, what was not in the original piping diagram is this little guy right here. Look at that. That is a basket strainer. And in the original diagram, they did not show a basket strainer. So the basket strainer was added after the fact, and the photographs revealed that there was some kind of device, and I could see it in the photographs, between the cooling tower and the suction side of the pump. And I asked what that was, and it turned out to be a basket strainer. And so when we did the pressure drop calculation, when we did the pressure drop measurements, we took the pressure drop across the basket strainer, and we found out that the pressure drop was greater than what was anticipated. And that, in fact, was the problem. So it wasn't a pump issue, it was a system issue. And the problem was that the basket strainer had a much higher pressure drop than that was anticipated. So we helped the customer solve the problem. We helped them understand that it was not the pump, but that it was, in fact, the system problem. The pump curve the data they gave us on the pump curve, it turned out to be accurate. It was, in fact, 750 gallons per minute. They did have a 92-foot pressure drop instead of 80-foot pressure drop across the pump, and or the differential pressure, which means that the strainer had It's because 92 minus 80 had a 12-foot pressure drop. The published data for the strainer, by the way, in this particular example was about 2 feet, but for some unknown reason, the actual pressure drop that was measured in the field was closer to 12 feet, and that was the problem.
So someone said that's because there was a rag in it.
It could have been. The point here is that once we sort of narrow things down to where the problem was, in this case, the basket strainer, then we're done. As far as TACO is concerned, we've helped the customer identify where the problem is. It's now up to them to sort out their basket strainer because it's got nothing to do with the pump. So unlike the original conclusion, there's a problem with the pump, turns out there was not a problem with the pump. It's actually a system issue, and in this particular case, it happened to be a basket strainer.
I don't want to throw stones, but it's not, I would say upwards of 80 to 90% of the time, it's not a problem with the pump and it's a system issue.
That's correct. The overwhelming majority of issues that we have to resolve are system issues. That doesn't mean we don't have a pump issue from time to time, but on a statistical basis. When we start the troubleshooting process, the whole process that we described here, we try not to draw any conclusions at the beginning because it could in fact be a pump, but we don't know for sure, and that's why we have to get the rest of the data. Okay, so I want to go into some additional things to look for during the troubleshooting process. But do we have any questions about what we came up with so far, Brett?
Well, there is a leftover question here from Bryce. Aren't most pressure sensors static pressure sensors? I'm not sure where that fits in, but that's the question.
Yes, the pressure gauge is measuring static pressure in the system, assuming that it was installed properly. And to get a good reading, the gauge needs to be connected in, perpendicular to the water stream or the fluid stream. If you connect the gauge where it's and you're reading the total pressure, then you're reading the static pressure plus the velocity pressure.
So Bryce clarified that was related to the comments about correcting for fluid velocity differences. That makes sense.
Yes. So whenever you have a difference in outlet condition, outlet size versus inlet size, then you have to correct for the velocity pressure if you're looking for the static pressure differential.
So Mike says, would an oversized strainer solve the issue, or do you even need the strainer? You know, that's some decisions you got to make.
Right, and this was a real situation, by the way. I changed the numbers a little bit to make it easier to read, but this came up about 3 months ago, and it turned out it was in fact the basket strainer. But at that point, I ended the conversation with the owner, and I basically just said that, look, it's clear that the basket strainer is the problem. It's up to you to work with the basket strainer supplier. We didn't provide the basket strainer. It was not provided by our rep on the project. They bought it from someone else. And so we just basically narrowed down what the issue was to the component and then let them figure out what to do with it.
Yeah, sometimes it's hard to stop so you don't go too far, I guess is what I'm trying to say.
Right.
From our perspective, you know what I mean?
Okay, so any other questions, Brett, before we head along here?
No, you're clear.
All right, so here are some of the things to look at. When we're asking for measurements, as I have here on the left-hand side, I'll get my bouncing ball again here. On the left-hand side, what am I asking for measurements? Well, that data sheet that you can download, today's, what do we call that? Is it a downloadable document?
Yep.
I guess that's what it's called.
Yep.
Okay, so we're asking for this information. We're asking for the flow in gallons per minute, the suction pressure, the discharge pressure, the power, the horsepower, the kW, and if you don't have that data direct, then you'll have to take the volts, the amps, and do all those calculations that we talked about. It's also important to know what the fluid type is. We've run into this problem, by the way, a few times. the pump was selected as to operate pumping basically clear water, but in fact it was a chilled water system that was pumping a water glycol solution. And so the data was there was a mistake. They actually designed the system all based on glycol. I think a very common percentage is 30% propylene glycol by volume. But the pump was selected at 100% water, and so the pump was consuming more power than what was originally anticipated, and it turned out that it was because they had selected it with water, but they were actually pumping glycol. And then the temperature is important too, especially if you have glycol. If you have a chilled water system that's pumping water glycol solution, the temperature will have a fairly significant impact on the amount of power that it needs to move that water glycol solution. If the temperature is low in a chilled water system, it will have a significant impact. Turns out if the fluid temperature is relatively high, let's say it's 190 degrees, and it's a water glycol solution, it has very little effect on the power. So that has a piece of data. And like I said before, we want to know the volts and the amps and the RPM. And what do we need to correct for when we get this field data? Well, one of the things that we need to make sure is that we need to make the correction in gauge height. So in this little example here, we're measuring the suction pressure over here, and we're measuring the discharge pressure over here, and there's an elevation change in the piping system. I ran into this not too long ago where the elevation change, because of the way the gauges were physically installed and the way the piping was physically installed, there was about a 15-foot differential in elevation, but nobody told me. So when they said that the pressure, they gave me the pressure differential, I said, well, none of this makes any sense. And that's when I went back to the photographs, and sure enough, the photographs revealed that the gauge was at a different height. So you do have to make that correction for gauge height. We've already talked about the change in velocity. You have to make that correction. You have to know the motor efficiency and the drive efficiency if you happen to have a variable frequency drive. So those are the cool things that you need to know. You also need to have calibrated gauges. So this question comes up from time to time. So well, how do I know, how do I get a calibrated pressure gauge? Well, most suppliers can, before they ship the gauge to you, they can check the calibration. And I have a little photograph here of what the instrumentation looks like. Let's go over here for a second. So here's a conventional gauge on the left. I did want to point this out. This is a compound gauge in the center, and this is a digital gauge. So one of the challenges, especially in condenser water systems, this actually came up about 6 months ago. We had a customer call and they said, I'm getting zero pressure with the pump running at on the suction side of the condenser water pump. And he showed me a photograph of the gauge, and I said, it looks like the needle on the gauge is pinned. He said, oh yeah, it's reading zero. I said, well, you know, it's very rare that a gauge reads right on zero. It's probably less than that. So I asked him to remove that conventional gauge and install a compound gauge. And sure enough, when he put the compound gauge in, the dial actually went down to, I think it went down to like minus 15 inches of mercury. And so we were able to figure out that the pressure on the suction side of the pump was much lower than zero, and that was creating the pump, causing the pump to cavitate. So that was another issue. So especially on low pressure suction sides of the pump, it's best to put in a compound gauge than just a conventional gauge because it gives you a much better reading. And some of the newer gauges are the digital gauges. They're really good. They can read positive and negative values, and they can also read in PSI and in feet. So it's all kinds of good stuff. How do you calibrate a gauge? Well, this, I'm not going to go into a lot of detail, but this is an instrument for calibrating the gauge. So this is the reference gauge over here on the left. And then you see where it says gauge port, you screw the gauge into the gauge port, and then you turn, you pump up the pressure, and then you can fine tune the pressure with this rotating wheel here. And then you can really, so if you're looking for, let's say you wanted to calibrate this gauge, you would crank these pressure valves up until the reference gauge read, for example, 150 PSI, and that's what should read on the actual gauge. And then there are adjustments that can be made, which can be done by the gauge supplier or gauge manufacturer. So it's fairly simple and straightforward to get a calibrated gauge. And that's how you do it. Like I said, you put in the pressure that you're looking, you connect the gauge, you put in the pressure on the reference, and then you adjust the actual gauge to give you the reading that you're looking for. Oh, and by the way, let me just go back here. The other thing is that when it comes to gauges, since we use them quite a bit for information, you want to pick a gauge where the mid-range of the gauge is fairly close to the reading that you're looking for. So for example, in this one on the left, if the actual pressure, the black lettering here on the outside is PSI, let's say that the actual pressure that they were trying to read was 30 PSI. Well, in this particular case, you'd want that 30 PSI to be mid-range in this area over here. So the gauge might go from 0 to 60, and mid-range would be 30. And that would be much more accurate to have a gauge that's reading it at mid-range than it is way down here. They lose their accuracy down here. So try to select gauges that are appropriate for the pressures that are being read. Flow meters. So the two type that we talked about, one is a permanently installed insertion flow meter. This particular one that's in blue is an Onicon flow meter. We have several of these at the factory that we use for keeping track of our hot water and chilled water systems. And then the other type, which is typically not a permanent installation, but is used for troubleshooting, would be an ultrasonic flow meter, sometimes referred to as strap-on, and you can see the straps that are connected to the pipe. And usually these guys require a substantial amount of straight run of pipe to get an accurate reading. They usually need about 15 pipe diameters at the inlet and about 10 pipe diameters at the outlet to get an accurate reading. And so that we run into that from time to time, where somebody will come along and they'll say, well, we have this flow data, and you know, your pump is pumping 20% less than what it should be, and we're proving that with the flow meter. And then I get the photographs and I realize that they connected the ultrasonic flow meter on an elbow. So the flow comes vertically upward, makes a 90-degree turn, goes right into the flow meter, and then they have a valve at the discharge side of the flow meter that's throttled back. You can't get good readings with those kinds of field conditions. So it's important to know what the limitations are of the instrumentation.
Are you quietly suggesting you need to read the instruction sheets of the flow meter?
Well, you know, I mean, we get, when you deal with this on a daily basis, you get all kinds of things. And I would have to say that the overwhelming majority of data that we get from the field is pretty good. People know what to do, they know how to do it and so on. But if we get wacky readings, then we start digging, and that's when you wind up with these crazy things where you wind up with an elbow at the inlet, a valve at the outlet. And yeah, you're right, Brett. When all else fails, read the owner's manual. Okay. So when we what we would like for a typical installation, well, we'd love to have a minimum of 10 pipe diameters at the inlet. In this particular case, it happens to be a 6-inch pipe, so we'd like to have 60 inches. And I can hear people screaming up and down right now, saying, "Oh, we can never get that." Which is why it's nice to have an end suction diffuser. If you can't get the minimum pipe diameters and you need to make an elbow, it's nice to have an end suction diffuser. They do a reasonably good job within their own limitations of straightening out the flow and providing reasonable entrance conditions. But keep in mind that when the pump is tested at the factory for the actual performance data that's published, it's done with a minimum of 10 pipe diameters at the inlet. Okay, this is the end suction diffuser. If we can get it, we'd like to get a spool piece between the suction diffuser and the inlet of the pump. We know that that's not necessarily a practical solution. We're happy to mount the suction diffuser directly on the pump. But anything that we can get that's a straight run of pipe between the suction diffuser and the inlet of the pump is going to improve the performance of the pump. Now, when it comes to an end suction diffuser, the performance doesn't degrade by that much. We know this because we've done some recent tests in the test lab with and without suction diffusers, and it does make a slight difference, but it does not have a major impact on the operating characteristics of the pump. So, so these are sort of ideal conditions that be nice to do it. And the other thing is we say pipe away from the pump. What we mean by that is that in this particular case, let's assume it's a rigid mount. There's a rigid pipe stanchion over here. There are flex connections up here. And all of this piping is done once the pump is placed physically with the base, and in this case, a housekeeping pad. Everything's bolted down and grouted and all that other kind of cool stuff. And then you pipe away from it, and then someplace over here, and I'll just kind of, let me see if I can do this. Before the pipe is connected to the system, let's say the system piping is over here somewhere. I'm going to kind of exaggerate that it's a little bit off, a little bit higher. So whatever correction needs to take place, it needs to take place out here so that you get a smooth transition between the pipe in the connected to the pump and the pipe connected to the system. You don't want to put any strain on the actual pump configuration itself. Always pipe away. So we're getting close to our time limit here, Brett.
We have a couple questions.
Okay.
So what's your opinion about to connect a differential digital gauge in the flange ports of the pump?
Well, we do, yes, we do recommend that for pressure readings that you take the pressure readings at the flange ports of the pump to get the most accurate readings. The challenge there is that sometimes we'll see people take the pressure reading. If I can exaggerate for a moment, let's say they put the pressure gauge over here on our little example. There's the pressure gauge right there. And that pressure gauge does not tell us what the pressure drop could potentially be through this piping, through this valve, through this flex connection, through the end suction diffuser. It'd be much more accurate to make the connection right here at the flange port. Hopefully
I've seen many MEP detail drawings showing it on the pump. So
yeah.
if possible, I would recommend, I think that's a good recommendation.
Yeah, because you have to, if you don't, then you have to take into account the pressure drop, and that's not always that easy to calculate. It's much easier to measure than it is to calculate.
So we have a comment here, you know, a good troubleshooting comment from Carmen. Many contractors don't realize that there is also a suction strainer in all cooling towers. Many times that is the culprit and not the basket strainer. Just a comment, you know, just
yeah,
another,
that's a good point.
Another thing to check.
Anything that can restrict the flow between the cooling tower and the suction side of the pump, especially in an open cell cooling tower arrangement where the cooling tower does not have a substantial change in elevation between the tower basin and the pump, could influence and in fact cause the pump to cavitate. So usually that's where we see the biggest problems in open cell cooling towers and the stuff that's connected in there.
Does strap-on sensors assume a clean pipe on the inside?
That's a very, very good question. Yes, so most of the manufacturers that provide these ultrasonic strap-on flow meters, you have a correction factor for the inside surface of the pipe. So you not only can select the pipe material, but you can also select the roughness, I believe, of the pipe. I know we have a strap-on meter, and that's one of the things that we have to put into the data. For example, if it happens to be copper, we have to tell them the copper, the size, and we also have to take a guess at how smooth the inside surface is of the pipe. And so if it's brand new pipe, you can assume that the surface is probably pretty close to what the manufacturer is publishing. But if the pipe has been hanging around for 10, 20 years, and it's especially if it's something like condenser water, the inside surface of that pipe could be very, very rough. If you don't take that into consideration, you'll get false readings with your ultrasonic flow meter.
And then Here's a nice comment here from Heidi. She's thanking you very much for your presentation. Very similar to an issue we encountered commissioning low flow on 3 condenser water pumps with 3 cooling towers. So it actually is a practical presentation, Rich.
Yeah, I mean, one of the things I like about this troubleshooting tech tips is that, if we can get into a conversation with our audience, there's usually people have examples that we can work through and find a variety of solutions for them.
Well, that's it for questions, and it's 1:01.
If we have any last minute questions.
Nope, that's it for questions / comments. So I think we're at the end.
We're at the end, as they say. So when we're at the end, we say thank you when we're at the end.
As usual, Rich, great job. A lot of thank yous popping up on comments / questions. And look for more classes. We haven't come out with our next quarter's classes. Actually, we have one on vertical inline pumps in 2 weeks. So that's another one in March. So we haven't come out with ours in April yet. So you're welcome, everybody. Rich, great job. Take care, and we will see you down the road. Bye.